Hi, today we're going to talk about the electric field. We have three goals today. So we'll introduce the idea of the electric field. We'll look at the connection between the electric field and what we've done previously with gravity. And the third thing is we'll have a very quick look at diagrams that show electric field lines or electric field vectors. So we will start just with this analysis of this situation of three charged particles arranged in a line. Charge 1, we know where it is, but it's got an unknown charge, and we don't know the magnitude of the charge, and we don't know the sign on ball 1. Ball 2, we know everything about it. We know where it is, we know that it's a positive charge, and the magnitude of the charge is Q. So it's plus Q is the charge. Ball 3 is similar to ball 1. We know for certain that it's got a non-zero charge, but we don't know what the sign is. We do at least know where all the balls are. We know one more thing. Ball 3 is in equilibrium. It feels no net electrostatic force due to the charges on the other two balls. Knowing this, what can you say about the sign of the charge on ball 1, the one all the way to the left? It's ball number 3, the one all the way to the right, that feels no net force. Okay, so here's some possible answers. The sign of the charge on ball 1 is positive, negative, or 3. We cannot tell unless we know the sign of the charge on ball 3. So you have to think the best answer is to that. Okay, so let's analyze it and see. So if we draw a free body diagram of ball number 3 here, then we know it feels no net force. It's got a non-zero charge, and so it has to be feeling a force in one direction because of charge number 2, and it must be feeling a force in the opposite direction because of charge number 1. The only way that can happen is if charge number 1 has the opposite sign to that of charge number 2. Okay, so we can nail the sign down on charge number 1. It's got to be opposite. So if, for instance, charge 3 is a positive charge, then the arrow going to the right on the free body diagram of ball 3 is applied by charge 2, and the one going left on charge 3, if charge 3 is positive, is applied by charge number 1. If you flip the sign on charge 3 and make it negative, then both of those force arrows will flip, so they still cancel each other out. Okay, so we've established that even though we don't know what the sign of the charge is on number 3, the sign of the charge on number 1 has got to be negative. Okay, how about the magnitude? Can we figure out the magnitude of the charge on ball 1? Remember, we do not know what the sign or magnitude of ball number 3 is, its charge. Okay, so turns out we know enough because we know how far charge 1 and charge 2 are away from ball number 3. So charge 1 is 3 times as far from ball 3 as ball number 2 is. Ball 2 is R away from ball 3. Ball number 1 is 3R away from ball number 3. It's 2R from ball 2, another R over to ball 3, so a total of 3R. And of course the distance is squared in our force equation, K, Q1, Q2 over R squared, and so that factor of 3 in the distance gets squared to be a factor of 9. And so for charge 1 to be, for its distance effect to be 9 times less than that of charge 2, because it's 3 times further away, then its charge has got to be 9 times bigger than that on charge 2 to make up for that 3R all squared. So the ball has got to have, ball 1 must have a magnitude, a charge with a magnitude of 9Q, and it's got to have a negative sign. Okay, so we'll go through that again. We'll do the math. Okay, so let's say to the right is positive, and I'll show all the math, then we'll go through it. So first line says the net force on charge number 3 is the force that 1 exerts on 3 plus the force that 2 exerts on 3. Those are added as vectors. And add them as vectors, they have to equal 0. That's basically what our free body diagram of charge number 3 says. Okay, so the force that 2 exerts on 3 is K times Q, that's the charge on object 2, times the charge on object 3 over R squared. Now that works whether Q3 is positive or negative. If Q3 is positive, well, then that term is positive, and we get a repulsive force, and that's to the right, and we get the right sign there. If Q3 is negative, then that's going to tell us the force goes to the left, and that makes sense because if Q3 is negative and Q2 is positive, they will attract each other. And so Q3 will feel a force due to Q2, which is to the left in that case. Okay, so similarly, we can do something similar with charge number 1. We've got 3RL squared in the denominator. We've got K, I'm putting the absolute value of Q1 here times Q3, and then putting a negative sign out front. And that will actually make all the signs work out properly. Okay? So we know Q1 happens to have a negative sign. And that'll give us the right sign on that charge, whether Q3 is positive or negative. Okay, so when you put those together, the K's go away, the Q3's go away, the R squareds go away. 3 squared turns into a factor of 9 in the denominator. So we end up with almost everything canceling out, and we're left with the magnitude of Q1 divided by 9 is Q. So in other words, the magnitude of Q1 is 9Q, and we've already established previously that the sign on Q1 is negative. So putting it all together, Q1 has a negative 9Q charge. Okay, so let's have another look at this. And so the neat thing is, now remember the Q3 canceled out of our equation, right, when we did the force analysis. So the neat thing is that we don't need to know anything about ball 3 aside from where it is. Okay? The charge on ball number 3 could be absolutely anything, and the net force on that ball would be 0. Okay? So the charge, or ball 3 itself, isn't special. It's the location where ball 3 is that's special. Okay, so let's just take ball 3 out of the picture and think about that location where ball 3 was, and think about how separately object 1 influences that point where ball 3 was, and how object 2 influences that point. And their collective influences have to cancel out. Okay, so now we're heading into what we call electric field here rather than force. Okay, so when we had ball 3 in the picture, we said ball 2, for instance, ball 2's effect on ball 3 is given by Coulomb's law. F23 is KQ, the charge on ball 2, times Q3, charge on ball 3, over R squared. Now, here we can say, if you get rid of ball 3, you can say charge 2 has an influence on that point where ball 3 used to be, and that influence is given by what we call the electric field. So we can say E here for electric field. The electric field produced by charge number 2 at the location where ball 3 was is K times the charge on ball 2 divided by how far the point is from ball 2. That's R squared. Divided by that distance squared, that is. Okay. And ball 1's field at the location of where ball 3 used to be, we can do in a similar way. And by the way, field is directed away from a positive charge and toward a negative charge. So at the location where ball 3 used to be, the field, because of charge 2, will be to the right, away from that charge. And to the right, remember, we defined to be positive. So ball 1's field will be negative at the location where ball 3 used to be before we took it away. The field, because of charge 1, will be to the left, pointing back toward the negative charge. Okay, so that field is basically the force we used to have divided by Q3. So we took Q3 out of the picture. So field is force over Q. And so now we get k times minus 9q, charge on q1, divided by the distance squared, 3r squared. And it's negative because, again, it points to the left. Okay, so the factors of 9 on top, and then 3 squared gets us a 9 on the bottom. Those factors of 9 go away. And we get ball 1's field at the location where ball 3 was. That's shown by the dot in the picture. That's minus kq over r squared. The negative means it goes to the left. E2, at that point, has exactly the opposite field, plus kq over r squared. In other words, kq over r squared pointing to the right. And so the two fields, which are vectors, each field is a vector, cancel each other out. Okay, so here's our first introduction to electric field. Okay, so just to cover some general things about field, actually, not just electric field. A field is something that has a magnitude and direction at every point in space. And in fact, we're familiar with something like that, and that is the gravitational field, which we symbolize by G. Okay, so if you look around you, wherever you are right now, you look around, every point nearby you has a value of G. It's usually near the surface of the Earth, about 9.8 meters per second squared directed down. That's true at every point in space in your vicinity, most likely right now. So we often called G the acceleration due to gravity previously, but a better name for it actually is the gravitational field. So if you're used to working with G, then this thing E, the electric field, plays the same role for charges that G does for objects with mass. Okay, so if you're familiar with G, you should be fine working with E. Okay, so let's go over how we worked with G before. If only the gravitational force acts on an object, you throw a baseball into the air. Once you let it go, the only thing acting on it is the force of gravity. And so we can say the sum of all the forces, simply mg in that case, is ma. And then the m's cancel, and so A equals mg over m, which is just G. Okay, so G is both the gravitational field, and it also is equivalent to the acceleration in that case. Okay, so slightly more complicated with a case where you have a charge acted on only by an electric field. Okay, so in that case, we apply a similar idea. The force, because of the electric field, the electric force, in other words, instead of being mg, it's QE. Okay, so Q plays the role of m, E plays the role of G. Okay, so the force that the charge feels, charge is a size Q in a field E, is QE. We set that equal to ma because it's the only force we have. And then we solve for A. And so before we had A as mg over m, and the m's canceled. Here we have A as QE over m, and nothing cancels out. Okay? But the acceleration is derived in a very similar way by basically drawing the free body diagram. It's only got one force in each case on it, setting that one force equal to ma, Newton's second law, we're doing here, and solving for A. Okay? So we're treating E in the very same way we're really treating QE the same way we treated mg, actually. That's maybe a better way to say it. Okay, so there we have field. But the bottom line is, if you're used to working with G, little g, then this thing E, you treat in a very similar way. Okay, so here's things we often draw here. So these are field line diagrams. These give very qualitative ideas for what the field looks like at various places. And generally, the closer the lines are, the stronger the field is. Okay? So what is picture A showing? Well, picture A shows equally spaced field lines. They're all going the same direction. They're all equally spaced. So that's what we call a uniform electric field. It's directed down, obviously, because the arrow heads are down. That's much like the gravitational field near the surface of the Earth. Okay? Basically, in the room you're in now, wherever you are now, the gravitational field vectors look a lot like that. Gravitational field lines running into the Earth's surface look like that. Okay, picture B is the field near a point charge. In fact, a negative point charge, because field lines end on negative charges, they start on positive charges. Okay, so picture B shows the field increasing in magnitude the closer you get to the charge, and the field lines get further apart as you get further away from the charge, so the field is less further out. But that field line picture gives you a general idea of what the field is, how strong it is, and what direction it is at every point. Now you note the arrows don't go through every point in the diagram. That doesn't mean that at points where the arrows don't go through, there's no field. That's not what it means at all. Okay? You could rotate those arrows by 5 degrees, 10 degrees, 30 degrees, whatever you want, and if you could draw them going through any point you want on the diagram. Okay? So just giving you a general impression of how strong the field is and which direction it goes at every point. Okay, so C is a little more complicated. We have both a positive charge, that's the red thing, and a negative charge, the blue thing. They happen to be equal in magnitude and at different locations, so we call this an electric dipole. Two charges that are equal and opposite separated by some distance. That's an electric dipole. And so all the field lines that start on the positive charge end up ending on the negative charge. And the field lines curve around. Okay, if the positive charge was there all by itself, you'd have a very symmetric picture similar to B with the arrows going away from the positive charge. But the fact that this negative charge is nearby curves the field lines around. Okay, and then we can also talk about an equivalent representation we called field vectors. Okay, so then we basically pick sort of a grid of points and we draw a little arrow representing the field at each one of the grid points, okay, nearby. So in the uniform field, we have all these little vectors of the same size, equally spaced. In picture B, we've got little arrows all pointing in toward that charge, that negative charge. That tells you it is a negative charge because the field goes in toward minus charges. And the darker the arrows are, in this case, the stronger the field. So the closer you get to the charge, the bigger the field gets. Okay. And C, similar thing. The closer you are to the positive charge, the bigger the field is. That's the darker the arrows there. And the field goes away from the positive charge, and the field points toward negative charge. Okay. So, you know, those are lovely diagrams. However, if you're asked about the electric field at a particular point, we want to know quantitatively, calculate exactly what the electric field is at a particular point, then you generally don't use your field line or field vector pictures. Okay? So in many instances, these are not terribly useful. And instead, we use a method that we basically were using at the beginning of this video, where we say, okay, here's the field due to object 1, here's the field due to object 2, and we simply add those fields as vectors. And if we had 17 charges, we would figure out 17 individual field vectors, and we add them all up as vectors to find the net field. Okay, so just vector addition once again, which we have lots of experience doing. Okay, so don't get too caught up in the field vector or field line picture. It gives you a very qualitative view of what's going on at various points. But if you want to get quantitative about a particular point, really, you can often just forget the field line or field vector picture and just do some calculations based on what individual charges are doing. Okay, we often call these point charges because in general the charges are small in comparison to everything else in our picture. Okay, and again, the electric field from a point charge has a magnitude of kq over r squared. Q is the charge of the point charge itself. And this thing creates a field at every point in space nearby. And the field it creates at the point depends on how far the point is from the charge. So r is the distance from the charge itself to some point where you're interested in calculating the field. That's the magnitude, kq over r squared. And again, the direction is away from a positive charge and towards a negative charge. So you say, okay, here's a charge at some location. I'm going to pick a point nearby. The field at that location nearby is away from the charge if it's positive, back toward the charge if the charge is negative. Okay, so there's a little bit of an introduction to field. Okay, but the most important message to take away here is A, you've got lots of experience with field because you've dealt with gravity before. Okay, so B, don't forget that. You know, if you're comfortable dealing with little g, then you handle E in a very similar way. Okay, so that is all for today and electric field.